We've looked at Earth. There's another celestial body about which we know almost as much as we know about Earth. It shares with the Earth the amazing fact that it's been visited by humans. This is our moon. 12 people in total have visited the moon. And this means that we have samples of lunar rocks and soil that were brought back. As we'll see, this is not unique to the moon in that sense. Bits of other planets have been knocked off by impacts, and some of them have eventually found their way to Earth, so that we have meteorites whose source can be traced back to Mars or other planets. But the samples brought back from the moon were brought back from precise positions. We know where they came from, and this will become important. And there are experiments that the astronauts left upon the moon, and so we should know quite a bit about the moon. It's a good place to test what we learned on Earth and apply it to another similar, smaller object. And let's start by looking at the moon. The moon, as we know, has two sides. As it orbits the Earth, one side always faces the Earth. Looking at these images, it's pretty easy to recognize the familiar man in the moon face on the left. That's the near side. The far side is missing those dark splotches. They're called maria because originally they were assumed to be oceans. We now know that there is no water on the moon. We talked about there couldn't be water on the moon. These are not oceans, they're lava flows, but the name maria sticks. Regions of the moon that are not maria are called highlands, and we see from this image that they're heavily cratered. This is true. The far side is all highlands, and the distinction, the dichotomy between the far side and the near side, the causes for why one side is different from the other are not, I think, clear in any sense that I can explain it. And so we'll just leave the statement at that. It certainly has something to do with the presence of the Earth on one side, but what exactly is far from obvious. Let's take a closer look. There are beautiful lunar maps. Let's take a closer look at the surface of the moon and see what we can see there. This is one of the benefits of having had so many spacecraft orbit the moon. We have brilliant photographic maps of the moon. I'll post a link to this one. You can play with it if you'd like. And here we're looking at the region of the Mare Crisium, one of those maria that I spoke about. And we can see that while it's not an ocean, it does share the properties of an ocean. It looks kind of like it. It's flat and straight and dark. And whereas the highlands around it appear to be peppered with craters, and we see that this mare appears to be a crater in its own right, except a very large crater. Indeed, when astronauts investigated the mare, it became clear that what these are old lava flows. These are traces of old volcanic activity on the moon, not in the form of large dome volcanoes like on Earth, though there are traces of that, but mostly lava flows that essentially flowed and filled a existing large crater. You will notice that the highlands surrounding the mare are heavily scarred with craters of all sizes, but few as large as the maria. And so we begin to be developing an understanding of time, and we see that there are craters inside the mare, but they are few and far between. What we take this to mean is that the terrain of the mare is more recent, the moon has been under constant bombardment, and the mare only has craters reflecting those impacts that have occurred since the time it was resurfaced by the lava flow. This is why terrain in the maria is by and large smooth, because it is younger terrain. So we've learned something about how to learn about the age of terrain. Older terrain will have more craters. The longer something is sitting there, the more impacts it will absorb. This, of course, terminates at some point. You reach some saturation where new impacts destroy as many craters as they produce. You can get a little more refined sense of dating. We focused here a little bit to the north of the Mare Crisium on this crater called Cleomedes. We've made a little bit of an enlargement. And what we can see is that Cleomedes is itself a large and rather old crater, and it's been degraded. Its rim is not very sharp and not very high, and indeed, on its western rim, I'm using conventional east and west notations here, is this crater Tralles, which clearly postdates Cleomedes. The impact that created Tralles postdates the impact that created Cleomedes, because Tralles obliterated a part of the rim of Cleomedes. And similarly, going up here to the north, we see that Cleomedes E postdates Cleomedes, and Cleomedes A, this nice sharp round one, postdates Cleomedes E. And so, because we have craters upon craters upon craters, and if we magnify further, we can see yet more craters upon them, what we can see is that we can begin to order things in terms of the order in which they occurred by not only the degree of cratering, but also precisely ordering the craters one on top of the other. Enlarging still further, we see that when I said that the interior of Cleomedes was relatively unscarred, relatively was the operative word. Indeed, this is a region which is less cratered than the surrounding, but there have been impacts inside Cleomedes. We also see another typical lunar feature, these rima Cleomedes. These are these ridges which are thought to have formed when the interior of the moon cooled and contracted, the crust having already solidified. This is the closest analog the moon has to plate tectonics. We do not find on the moon, aside from the impact craters, any indication of, and the volcanism, but any indication of linear features that would indicate plate tectonics. The moon's crust is all one plate. The moon is geologically inactive now, not completely. It's geologic activity such as it is that as the moon is shrinking, we get these linear features that are these ridges, which are basically the result of the surface shrinking as the interior cools. But the moon shows traces of past geologic activity, but certainly no current geologic activity. What we saw, lunar craters are created by impacts. This is the mechanism by which the moon is weathered, a continuous barrage of impacts, no atmosphere to protect it, and so even small rocks make it all the way down to the lunar surface. The maria are lava plains. Often they end up filling old, large craters. We see that there are old craters, and then it seems that with time the size of impactors has become smaller. Large impacts are always contained inside smaller ones that are more recent. So there is a progression in the size of the things that are crashing into the moon. We saw these rima or riles and graben that result from the shrinking of the interior. There's no volcanism currently on the moon. This makes sense. The moon is a smaller object than the Earth. It will have cooled. The interior will have managed to radiate out its heat sooner, and at some point, given enough time, the Earth too will become volcanically inactive. On the moon, this has already happened. So small planets we expect will cool faster just because of scale. The moon has essentially no atmosphere. Its gravity is not enough to bind an atmosphere. Such molecules of gas as are found on the moon will be exposed in the absence of both a global magnetic field, as we will see, and atmospheric protection will be dissociated by the sun's ultraviolet radiation. And so, for example, if there's any water vapor on the moon, the molecules will be broken up by ultraviolet radiation. The hydrogen atoms will be unbound and they will escape to space. The temperature on the moon, well, the moon is kind of like the easy model of the Earth we studied before. It has actually a very small albedo, and it's roughly a black body. There's no greenhouse effect. So the temperature we expect will be a little bit under 300 degrees. It's in the same orbit around the sun as Earth is. The thing that the absence of an atmosphere does is that there's no mechanism for shifting heat from the day side of the moon to the night side of the moon. Remember that lunar days and nights are 2 weeks long, and so you develop a huge temperature differential. Temperature is as high as 370 Kelvin on the day side, as low as 100 Kelvin on the night side, and in the deep dark shadows of some craters where the sun literally never shines, the coldest temperatures known in the inner solar system have been measured down to 35 degrees Kelvin, which is very cold indeed. There's clearly no water on the moon, because water, as we saw, requires atmospheric pressure to maintain it, but we have very good evidence that in some of these craters of eternal shadow, there are significant quantities of water ice, presumably imported on the same large bombardment that imported water onto the Earth. And the crust of the moon is very old. We see that it carries the traces of impacts, generations and billions of years of impacts. On Earth, that same amount of impacts, at least the larger ones, must have occurred. On Earth, this record has been erased by tectonic activity since the moon ceased geologic activity. in some sense, is a museum of the history of the solar system for the past 4 billion years or so. And in the highlands, the effect of these impacts has been basically to cover the entire surface of the moon with a thick layer of very fine dust, which is basically rocks that have been pounded to dust by impacts, and then also the effect of ultraviolet radiation. And so this is the regolith, the fine dust in which that beautiful footprint we saw was created. And so we can use the moon as a museum of history, and when we put together the ability to date crater and order craters by their size and their relative position, together with the fact that we have lunar samples whose provenance is known and we can radio date them, we can now identify which craters were created when, and then use that to find the dates of other craters. And we have bombardment history. We can construct a history of the rate at which the moon was bombarded, starting from the present and the most recent craters that we see, and into the older craters that we found. And we see that the rate of lunar bombardment, and you see that none of this is perfect, science is an approximation to truth, has been relatively constant for the past 3 billion years or so, but it appears that about 3.9 billion years ago, there was a phenomenon first described as a lunar cataclysm. Now it's known as the age of heavy bombardment. The NEISS model very nicely explains it. As you can see, not everybody agrees that that is what happened, but we have evidence that the moon was heavily bombarded about 3.9 billion years ago, and there are reasons to imagine that perhaps this was in fact a spike, as the NEISS model would suggest. One of the main reasons we believe in the predictions is that it agrees with this dating of moon rocks. There's more detail than is apparent in what I have said. Careful geologists have been studying this thing very carefully over decades. This is what we learned from the lunar surface, what goes on inside. The moon melted, it's a round object, there's chemical differentiation. There is a core, but the lunar core is anomalously small. The moon's total density is not much larger than that of rock. Once we conclude that it has a very small core, we study the moon's internal structure the same way we do the Earth's. There are moonquakes, in this case not generated by plate tectonics, because that's not happening, but mostly by the tidal forces of Earth causing internal friction. And we see that the moon's core is anomalously small, and its mantle very thick. The moon lacks a geodynamic magnetic field. There are traces of magnetization on the surface, but no global magnetic field. This has to do with both the slow rate of rotation and the fact that it's essentially done cooling. And while there is a fluid inner core, a solid inner core and a fluid outer core, there's not enough convection heating to drive a magnetic field. And the last important question, obviously, is where did this thing come from? How is it that Earth, of all the terrestrial planets, has a moon that is so anomalously large compared to the moons of other planets, and even compared to the Jovian planets? No planet has a moon so large by comparison to the planet. It turns out that the isotopic composition of the moon suggests that it's basically a piece of Earth. The relative concentrations of various isotopes of oxygen turns out to be a sensitive trace of where in the solar nebula something was formed. On the moon, they track those on Earth so precisely that the conclusion is that moon is literally a piece of the Earth. How did a piece of the Earth come to be in orbit? The most likely theory is that there was what was called a giant impact early in the Earth's history, before the solar system got cleaned up. Something either the size of Mars or perhaps a little larger crashed into the Earth. The impact vaporized large fractions of both objects, and if you get the dynamics of the collision right, as we will see, then the impacting object, which is not part of Earth and therefore doesn't have the right isotopic ratios, will be absorbed into the Earth's core, and mostly bits of the mantle of Earth will be spewed out into space. And this would explain both why the moon is poor in iron relatively and not that dense, because it is made up of the ejecta from this collision, whereas the core, the heavier material, sank into the core. We should look at this next simulation and see what it does. This is a very recent simulation. This is a recent version of the giant impact hypothesis that created the moon. And what we see here is that in this simulation, the Earth starts out with a rotation period, a day, a sidereal day of 2.3 hours. This is something to pay attention to. Remember that near-Earth satellites orbit the Earth every 90 minutes. The Earth is rotating so fast that rocks are almost in orbit. The Earth is on the verge of falling apart in the way the simulation works. This is important because it is the reason that this impacting object with a mass only 5% of Earth's mass, crashing into Earth essentially head-on, leads to a cataclysmic collision. The impactor is essentially absorbed by the Earth, and within 24 hours there's this cloud of what was formerly the Earth's mantle scattered around the Earth. And out of this cloud, we now have protoplanets and the standard accretion disk model. The moon will eventually form. Note that the moon forms in these models very close to the Earth. We've talked about George Darwin's theory about how the Earth is transferring angular momentum to the moon and slowing down. Earth's day, by the end of creating the moon, was about 2.5 hours in this model. And then over time, it turns out the entire Earth-Moon system exchanges angular momentum with the sun because of the sun's tidal forces over tens or hundreds of thousands of years. The moon settles down into its nearly circular orbit about the Earth. And then from this moment on, and the Earth has developed a day that is relatively generous, 5 or 6 hours. And then the process from here on is the tidal transfer of angular momentum from the Earth to the moon, which moves the moon farther away from Earth and leads to the 24-hour day that we observe today. One of the nice things that has been verified is that astronauts on the moon left reflectors there. We can measure the distance to the moon very precisely, and indeed, the moon is receding from Earth at a rate of about 3 centimeters per year. As I told you once, total solar eclipses are something to enjoy because they won't last.